Hello everyone, and thanks for watching Edupedia World videos. This is the fourth video in the chapter Current Electricity, and in this video we learn about many devices that are used to measure quantities in a circuit, like current flowing through a wire or potential difference across 2 points. Many of these devices, like voltmeters, ammeters or potentiometers, use a very simple concept called the Wheatstone bridge, so let's look at that first. And in discussing this Wheatstone bridge, I'm going to use one of those devices called a galvanometer. But right now you don't need to know anything about that device, except that all it does is measure the current flowing through a point, and it has a needle, and if the needle deflects, that means a current is flowing through the wire, and if the needle doesn't deflect, that means the current is not flowing through the wire. So this is the galvanometer. Yeah, so let's say we have 4 resistances, R1, R2, R3, R4, and we have a battery of EMF V, ideal battery, and it applies a current which flows through these wires. Now we keep changing one of these 4, or all 4 if you wanted, and we keep adjusting the values of these resistances such that there is no deflection within this galvanometer. That means we keep varying the resistances until there is no current flowing through this wire. If there is no current flowing through this wire, then these 2 points have to be at the same potential. Let's say that potential is V0. These 2 have the potential V, and these 2 have the potential 0. Remember, this is something I always do. I always start with taking the lower terminal of the battery, of one battery at least, to be potential 0, and that allows us to calculate all the other and reduces one variable. Otherwise I would have had V1, V2, V3, and V3 minus V1 is equal to V. Right? So now we need to find out the combination, the relationship between these 4 resistances in which there is no current flowing through this segment of the wire, that is, these 2 points are at the same potential. Right? So let's just write down the simple equations. Let's say current I flows here, so this is I1 and this is I minus I1, and this is I1 and this is I minus I1, and this is again coming back I. Right? So here we've used Kirchhoff's current rule, saying that the current flowing into the point through these 2 wires is equal to the current flowing out of the point. Right? So the first point would be V minus V0 is equal to I1 R1. Then the equation will be V0 is equal to I1 R2. Then we'll have V minus V0 is equal to I minus I1 times R3, and V0 is equal to I minus I1 times R4. Right? Now from this we'll just divide the first 2 and the second 2 equations. So what we'll get is V minus V0 by V0 is equal to R1 by R2 from the first 2 equations, and from the second 2, V minus V0 by V0 will be I minus I1 will cancel, and it will be R3 by R4. So from that we get the relation R1 R4 is equal to R2 R3. Or the the products of the opposite resistances are equal. The product of these 2 resistances is equal to the product of these 2 resistances. Anytime that is true, then these 2 points will have the same potential and there will be no current flowing through this wire. This can actually be used to measure an unknown resistance. For example, if we have one resistance R which we need to measure, we'll take 2 known resistances R2 and R4, and we'll keep changing R3 until there is no deflection within this wire. Then we'll have a particular relationship between R, R2, R3 and R4, and we already know these 3, so we'll be able to calculate the unknown resistance. Right? So this is something you'll see again and again. Whenever the product of these opposite resistances are equal, then there will be no current flowing through this wire, and these 2 points will have the same potential. Let's look at how this concept can be used to measure the potential difference across any 2 points or the current flowing across any wire. So first we'll see the device which is used to measure electric current across a wire, and that device is called an ammeter. And next we'll study the device used to measure the potential difference across 2 points, and that's called a voltmeter. Now both these devices work on the principle of a galvanometer, which is something we'll study once we've covered magnetic field, because the concepts of magnetic field are used to design that. Right now all we need to know about an ammeter is that it's a device in which you have two terminals. Like this is how an ammeter is generally represented. You have two terminals and you just connect this to a wire in series, and it will measure the current in the wire by having a needle, and that needle will deflect according to the magnitude of current. Right. So we need to put this in a circuit to measure the current across the wire. So I'll just draw a completely random circuit just to show you how this ammeter would be used. This is a resistance. I'll maybe add a capacitance as well. We'll see both capacitances and resistances in a circuit in the next video. Maybe I'll have a battery. Maybe I'll have another resistance here. Maybe I'll have a capacitance here. Anyway, it doesn't matter. So some circuit. And let's say we wanted to measure the current flowing through this wire. So what we'll do is we'll attach an ammeter in series in this position. So instead of this, it will end up looking like this is the original resistance, and this is where we'll attach an ammeter. So then when the circuit starts working, there'll be a needle in the ammeter, and instead of pointing at 0, it will point at some other value which will tell us the amount of current flowing through this wire. Right. Now generally what we do is if this ammeter has some resistance, let's say R, then this ammeter will change the resistance of the complete circuit. And what will happen is, just by the fact that we attach this ammeter of a resistance R into this circuit, the current flowing through this wire will change. Now there is no such thing as an ideal conductor. Every wire has resistance no matter how small, and an ammeter also has resistance because it's made up of wires. Right. So if there is a resistance in the ammeter, it will change the amount of current. Initially, let's say 10 amperes of current was flowing, and we attach an ammeter which has some resistance, and because of that resistance, now 9 ampere of current is flowing. So the ammeter will give us a reading of 9 amperes, even though before attaching the ammeter, the current was 10 amperes, and we needed the value of 10 amperes. So what is the solution to that? We try to make this resistance as small as possible. Right. So how do you make a resistance as small as possible? Well, there's one very clever way to do it. We know that when two resistances R1 and R2 are attached in parallel, the net resistance is R1 R2 by R1 plus R2. Right. We've just used the formula 1 by R is equal to 1 by R1 plus 1 by R2. Now look at this from this point of view. This is R1 multiplied by a fraction, and that fraction is R2 divided by R1 plus R2. So that fraction is obviously less than 1. That means this new resistance is less than R1. Similarly, this resistance is R2 multiplied by a fraction, and that fraction is R1 by R1 plus R2. So it's not only smaller than R1, it's smaller than R2 as well. And this always happens in series. In parallel. In parallel, if you add a number of resistances, then the equivalent resistance is smaller than the smallest resistance in them. Right? And if you add them in series, then the equivalent resistance will be larger than the largest resistance. So all we need to do is, let's say this ampere has its own internal resistance R. Right. So this is the actual ampere. Just like we can draw a battery, and next to it we can draw the internal resistance of the battery, even though it's actually present within the battery. This is how we can draw an ammeter. Now all we need to do is we need to attach another resistance in parallel with this whole device, which has a resistance small r, such that small r is much smaller than capital R. So if in this device, this is the original device, we just decide to show the resistance as well, because there will be resistance. If we attach another incredibly small resistance in parallel to this, then the equivalent resistance will even be smaller than this resistance. So it will be very small. And if the resistance is very small, the equivalent resistance of this thing, now it's not R. Now it's small r times R by R plus R. So it's even smaller than small r, the equivalent resistance. So that won't end up changing the current in the circuit a lot, and you'll get a more accurate reading. So if initially the current went from 10 amperes to 9 amperes, now the current might go from 10 amperes to 9.99 amperes. because this resistance is so small that it doesn't end up changing the current in this wire. And this is the difference which we can live with, or if we wanted to, we could make it more accurate. So that's one. And by the way, this resistance is called a shunt resistance. A shunt resistance is a resistance which is added to either an ammeter or a voltmeter to get desired results. So in this case, we have an ammeter, and in ammeter, a shunt resistance, a small shunt resistance in parallel is attached. So we have an ammeter with its original resistance, we attach a very small shunt resistance in parallel with it, and that greatly reduces the equivalent resistance of this system. Now once we attach it into the circuit, the current will not change significantly and we'll get a much more accurate reading. This is not the only advantage of using a shunt resistance. What happens is, because in creating an ammeter we use magnetic fields, ammeters are generally very sensitive to current. So for example, a general ammeter might read a current between 0 and 10 amperes. That means the minimum current it can read is 0, obviously, and it can read a maximum of 10 amperes. If the current flowing through the ammeter or through the wire is 100 amperes, then it will not properly function. Right. So what if we really wanted to measure a current which is, we know, around 500 amperes? So this thing works there as well, because when we say 0 to 10 amperes, that means the current flowing through this particular part of the ammeter has to be between 0 to 10 amperes. Now let's say a total of 500 amperes of current is flowing. Because this is a large resistance and this is a small resistance, most of the current will flow through this side. So maybe 495 amperes will flow through this side and 5 amperes will flow through this side. The smaller this resistance is, the greater the part of 500 amperes will flow through this side. Right? If both these resistances were equal, then it would be 250 amperes on each side. As we lower this resistance, more current will flow through this side. And now we see that even though the current through the wire is 500 amperes, the current flowing through the ammeter is only 5 amperes. So that means we could actually measure a current up to 1000 amperes in this case. So these are two advantages of attaching a shunt resistance. The first is it reduces the resistance of this whole system such that it alters the current less. And the other is, we are able to measure a greater range of currents because only a fraction of the actual current, and a fixed fraction because that fraction depends on R and R plus R. Right? This completely decides what fraction goes into which side. So this is a constant. So we only make a fraction of the current go through the actual ammeter, and based on that fraction current we can multiply it to get the original value, and we are able to measure a wider range of electric currents. Now a voltmeter is pretty similar to this with a few small differences. So I'll just write the differences first. In an ammeter we attached a small shunt resistance in parallel. In a voltmeter we attach a large shunt resistance in series. Now why do we do that? So first of all, we need to realize that an ammeter is always attached in series, right? So if this was the circuit, let's say this was a part of the circuit and we needed the current in this wire, then we attach the ammeter along with the shunt resistance in series to the circuit, right? This is a complete circuit. There's a lot of stuff here. Right. So this is how you measure current. You attach it in series with the wire. There is no other way to do it. How do you measure voltage difference? That is across 2 points. So let's say you wanted to measure the voltage difference across these 2 points. Then you would attach a voltmeter in parallel. Right. So there's another difference here. Ammeters are attached in series, obviously because we need to measure the current. This should be intuitive to you. This should not need to be remembered. That's why I didn't write it. Ammeters are attached in series because they measure the current. Voltmeters are attached in parallel to the points because they measure the potential difference across a point. Now we encounter the same problems with voltmeters as in ammeters if the voltmeter has a small resistance. Right? In this case, the script is completely flipped. It's small instead of large. So if the voltmeter has a small resistance, then if there's, let's say, 10 amperes of current flowing through this wire and the resistance is 5 ohms, in that case the potential difference across these two would be 50, right? 50 volts. Now let's say I attach this voltage in parallel, and once you attach this voltage, out of this 10 amperes, 8 amperes goes through this wire and 2 amperes goes through this wire, because again like everything in this world, a voltmeter has to have some resistance because it's made up of wires. So let's assume that it has a resistance such that 8 amperes goes in this direction and 2 amperes goes in this direction. Now what is the potential difference across these 2 points? It's not 50 volts, it's actually 40 volts. Using Ohm's law, V is equal to IR. So we see that if this voltmeter absorbs some current, lets some current flow through it, then that will change the potential difference across these points. So what would an ideal voltmeter do? An ideal voltmeter would, maybe if 10 ampere was flowing, then 9.99 ampere would go through this side and 0.01 ampere would go through this side. In that case, the potential difference across these 2 points would be 9.99 multiplied by 5, and that would be much closer to 50. So for a voltmeter, what we need is, the voltmeter needs to have as small a current flowing through it as possible. So how do you get to do that? You increase the resistance of the voltmeter. The smaller the resistance of the voltmeter, the larger the fraction of current will flow through it. The larger the resistance of the voltmeter, the smaller the fraction of current flowing through it. Now a voltmeter will obviously have some resistance depending on its, it should be V. A voltmeter will obviously have some resistance depending on its material. How do you increase that resistance? You add a very large resistance in series, and this is the shunt resistance here. And this might probably be, I'll just use different terminology. This was R, the internal resistance of the voltmeter. You attach a large shunt resistance in series with it. Right. Once you've attached a large shunt resistance in series with the voltmeter, the net equivalent resistance of the voltmeter becomes very large, and it will absorb a very small amount of current flowing through it, and the potential difference across these 2 points will remain the same. Right. So these are the 2 major differences between ammeter and voltmeter. Ammeters are attached in series and they have a small shunt resistance in parallel. Voltmeters are attached in parallel and they have a large shunt resistance in series. Right. Now, the problem with these 2 obviously is, like I said, you will never have an ideal wire which has 0 resistance. So both voltmeters and ammeters will never give you a completely accurate reading, though we've actually gotten quite close to actual values in experiments. So there's another type of device called a potentiometer, in which the value is completely accurate because we're not actually absorbing any amount of current from the circuit. We are creating a second circuit, our own circuit, and attaching it to the first circuit and applying our own batteries and our own resistances. So we'll not be taking anything from the circuit, hence the value will be 100% accurate. And that device is called a potentiometer, and it uses the concept of a Wheatstone bridge, which is what we learned right in the beginning of this video. So let's look at a potentiometer. I'll just draw the diagram first. Yeah, so this is a battery, this is a standard switch, and when we plug in the switch, the circuit starts working, and when we remove the switch, the circuit is not completed anymore, so it doesn't stop working. And that's basically to reduce the amount of energy wasted when this circuit will keep on going through this resistance when we don't need to use it. And this is what is called a rheostat. And this is the symbol, and that's nothing but a variable resistance. So normally you would have a resistance and the circuit would be completed like this. All this says is that it's a variable resistance. You could basically put this arrow in the midpoint, so the resistance used in the circuit would be half the original value. You could put it at 1/10 the original place, so only 1/10 of the resistance will be being used. And since we know that resistance is equal to rho L by A, it is proportional to the length, right? Also, this is not a wire, this is not a conducting wire which has no resistance. This is the wire which has some resistance, right? So that's why I'll draw it like this. Then you have these points, let's call this point capital A, and here you'll have small a, and then let's say this is a point B which goes through a galvanometer and maybe attached at the end or maybe attached at some other point C. Now these 2 points are the points across which we need to measure the potential difference. So they'll be connected to some other circuit, right? I'll just not draw the circuit, but there'll be some big circuit here, and we'll take this will probably go on like this, the big circuit, and we'll take 2 points of the circuit, and we need to find out the potential difference between these 2 points. Now the interesting thing here will be, we'll not draw any current from this circuit. The current we'll draw will be from this battery. Hence, the current in this circuit, or the potential difference across these 2 points, will not be changed at all by us adding the potentiometer. So what we'll do is, let's say this whole wire from A to B has a resistance of R, right? Then we'll attach this point to this end, and this is a conducting wire, so they both will have the same potential, and this point is attached to a galvanometer, which can be attached to any variable point, right? We'll attach the variable, we'll keep moving this variable point, and we'll leave it at a place such that this galvanometer shows 0 deflection, right? So in that case, the potential of this point B will be the same as the potential of this point, right? Let's call it O. Once these 2 points have the same potential, and these 2 points have the same potential, all we need to do is measure the potential difference between A and O, and that will give me the exact potential difference between A and B. So if the total length of this wire is L, and this length is L0, or small l, let's say, not L0, then the resistance of A and O, between A and O, would be L by capital L times the resistance between A and B, right? If small l is half of capital L, the resistance would be half, because we know the resistance is proportional to the length, right? So this multiplied by the resistance between A and B will give me the resistance between A and O. Since resistance is proportional, given constant current, it's proportional to the potential difference. The potential difference between A and O will be L by L times the potential difference between A and B. So let's call the potential difference between A and capital B. So let's call the potential difference here V, and let's call the potential difference between A and B V0. So V will be L by L times V0. If L is half of capital L, we've kept it at the midpoint, and the potential difference between A and B is, let's say, 10 volts, then the potential difference between A and the middle point of A and B will be 5 volts. That means the potential difference between small a and small b will be 5 volts. Right? So this is the equation from which everything else will be derived for a potentiometer. So I hope this is properly understandable to you now. Now this method will only work if the potential difference between capital A and capital B is greater than the potential difference between small a and small b. And that's where this variable resistance comes in. We can always keep changing this variable resistance to create a situation in which the potential difference between these 2 points has to be greater than the potential difference between these 2 points. How do we do that? We decrease the resistance. When we decrease the resistance, the total current through this circuit will increase, and that will increase the potential difference between A and B by V is equal to IR. Right? Now this V0, sometimes people confuse it for the voltage of this battery. That's not true, because we have a variable resistance as well, so we do not know the if this is something, this will be a fraction of that, right? V0 is the potential difference between A and B. Now there's another way to calculate V0. Instead of going through this circuit, we can attach a known potential difference here. So let's say here we attach a battery of EMF E, right? In that, and the length here is L0 in that case. So we'll have E is equal to L0 by L times V0. Now this battery E is a standard battery whose EMF we know. We can measure L0 and capital L, so we will be able to measure V0, which is the potential difference between capital A and capital B. Again, the remarkable thing about a potentiometer, since there is no current flowing in this wire, no current is being absorbed from the big circuit in this circuit, and therefore this A and B will always have the same potential difference no matter what. So that potential difference can be E into capital L by L0. So from that we get the relation V is equal to E into capital L by L0 into L by capital L, and this is V0, right? So LL will cancel, and from that we get the relation V is equal to E L by L0. Right. And this process taking a standard EMF battery to calculate the potential difference between A and B. This is called the calibration of the potentiometer. Once you've calibrated the potentiometer, you can calculate the potential difference between A and B, and then you can measure the potential of any circuit between any 2 points. Now you could also, what you can do is you can compare the EMF of two different batteries like this. So if you attach a first battery, the equation you'll get is E1 is equal to EL by L naught, or say L1 for this case, and then E2 will be EL2 by L naught. From that you can get E1 by E2 is equal to L1 by L2. So if you know the EMF of one battery, you can measure the EMF of a second battery by connecting both of them to the circuit at different times and seeing the relationship between the lengths. Another very important use for the potentiometer is to measure the internal resistance of a battery. So let me just first draw the circuit that is used. So this is a standard potentiometer. I'll just always draw this wire like this to tell you that this is a wire that has resistance, as opposed to a standard thin wire which doesn't. So this point, this is capital A, this is capital B, this is small a, there'll be a point maybe small b, and between these we'll attach our battery, and the battery will have its own internal resistance. So let's say this is E, this is R. What we'll also do is we'll attach a known resistance, capital R, and another switch, and that will be in parallel with this, right? So this is a point B which we'll attach at different points. Let's say this is. So first what we'll do is we'll remove this switch. That means this circuit is not complete. If this circuit is not complete, that means there is no current flowing through this wire, right? If there is no current flowing through this wire, then the potential difference across A and B will be E. If there is a current, remember it is E minus IR, but right now the current is 0. So initially if you get a length small l, then you will get E is equal to L by capital L times V naught, right? Now we'll plug in the switch. So this is the symbol for a switch which is plugged in, and now the circuit is complete, right? So once this circuit is complete, the potential difference across A and B will actually be E minus IR, where I will be E by R plus R. Again, the good thing about potentiometers versus voltmeters, we are not absorbing any current from this circuit, so this circuit will just behave as a standard circuit with two resistances in series. Putting this value here, we'll get E minus I, sorry, this will be small r, no, this is this, E minus E by R plus R times small r, which is E into capital R by R plus R. This should be right. So this is the new potential difference, and this, let's say, is equal to L dash by L times V naught. So we divide these two equations. What we'll get is R by R plus R is equal to L dash by L, or if you simplify it, you'll get R is equal to capital R times L minus, I'll just write it here, R is equal to capital R times L minus L dash by L dash. So we know L dash, and we know R, which is the standard resistance we added, so we can measure the internal resistance of any battery, right? This completes potentiometer. In the next video, we'll actually see how to solve cases of circuits which involve both series, which involve both resistors and capacitors. Thank you.